Hello everyone, I'm Luca Ciman and I'm going to present you the research project I've done with Fabio Freddi and Nicola Tondini entitled Retrofitting Methods to Mitigate Progressive Collapse in Steel Structures. First of all, I will introduce the method of progressive collapse and why the interest about this topic is growing so fast these years. I will expose the case study and the choices that led to the construction of the numerical model. I will then show the analysis results about the original structure, the considerations behind the retrofit, and then the analysis results of the retrofitted structure, coming finally to the conclusions. Progressive collapse is the worst scenario that a structure might experience when exceptional events trigger an initial local collapse. If the structure is unable to activate an efficient load redistribution in response to that event, the loss of a load-bearing element may cause the overloading of few nearby elements, which in turn collapse, leading to a chain reaction, which is called progressive collapse. Inside the existing building heritage, there are some strategic and sensitive buildings for which cost-benefit analysis might deem worth a retrofit intervention, allowing for the structure to prevent progressive collapse. Different strategies have been proposed these years, in recent years, like cables, enhancement of key elements, so local reinforcement, or roof trusses. We went for roof trusses for different reasons. It has low influence of seismic behaviors since mass and stiffness, lateral stiffness are nearly unchanged. It is minimally invasive because its construction does not interfere so much with the ordinary functions of the building. And thanks to a properly designed vertical stiffness, it can activate a good distribution for multiple progressive collapse scenario. The purpose of this research was first to evaluate the actual performance of the original structure, then study the efficiency of the retrofit solution proposed, and then develop a standard design procedure, leaving room for a critical evaluation for the outcomes. The case study we choose is a steel moment-resisting frame with rigid and full-strength joints, designed according to Euro codes and the Greek seismic code, since the building is located in Greece. It is important to notice that the sections are reduced with the height, so high floors as smaller elements. The modeling goal in this case was to reproduce the resistant mechanisms involved in the progressive collapse scenario. OpenSys was used because of its computational performances on nonlinear analysis, really useful for the parametrical studies here required. Both global and local geometrical and mechanical nonlinearities were considered, and a three-dimensional model was built in order to account for the out-of-plane buckling of the columns. Plasticity was finally modeled as distributed for columns through fiber sections and as lumped for beams. The deformability of the beam column joint was accounted for through the Chisos model, a simplified model here in figure in blue, that concentrates into two rotational springs the stiffness of column flange and the web. Whereas the lumped plasticity in the beams was modeled using a special parallel plastic hinge model. It's called the one in red here. This model was carefully calibrated in order to simulate the coupled behavior between axial and flexural actions which occur in beams in large displacement mechanisms. For the model validation, a push-down experimental test available in literature was selected, on whose results the parallel plastic hinge model was calibrated. As we can see, the model well fits the experimental results in blue. The alternative load path method was used for progressive collapse analysis. The initial damage is simulated through the removal of a column In phase 1, you can see the presence of the column is simulated through the force RC, and design loads are applied. Then in phase 2, the removal is simulated by the gradual application of a force FC of the same intensity of RC, but of the opposite direction. The loads on the spans above the removal are amplified by the dynamic amplification factor as required by the American UFC standards. Some parameters were defined in order to monitor the status of the system. When the removal is complete, all loads need to have found an alternative path to the ground, basically. Hence, the definition of the load factor, lambda, as the ratio between the actual applied load, or the sum of the base reactions, and the target load, Q tot. The state of the column was monitored through their work ratio in axial behavior, and also at the same time the mid-node columns sway were observed. This is the performance evaluation of the original structure, where it's clear that the central base column has been removed. On the right side, there are the state parameters we were just describing before, so load factor, lambda, and the efficiency ratio or work ratio of the columns, and middle node columns sway, where on the horizontal axis there is the vertical deflection of the node above the removal. As we can see, the structure exhibits limited redistribution capacity since the adjacent columns underwent out-of-plane buckling before the removal could be completed, so lambda could not get to the unitary value. The internal axis distribution, the internal axis stress distribution highlights concentration of loads in the adjacent columns to the removal, whereas the external column is really unloaded, is much more unloaded. So retrofitting strategy should then aim to better redistribute loads in order to get a more uniform participation in the redistribution process. This is the truss model, the model of the truss to be applied on the roof. In order to get a design procedure, we need to investigate the influence of two main parameters which rules the stiffness of the beam: area of the elements and height of the truss. In order to obtain a simplified analytical solution for the stiffness, an assumption has been made, and diagonal members are deformable, whereas frame elements were rigid. And the outcomes show that the stiffness grows linearly with the area, but not with the height. And there is a limit height beyond which the stiffness doesn't increase anymore. Further parametric analysis was conducted only on the height of the roof truss. For the case studied, the stiffness grew up to a height of 7 meters. Performing the analysis of the whole retrofitted structure, a height of 4 meters was deemed sufficient because it enabled a good redistribution, which allowed the total removal of the column, which was the target performance we was looking for. This is the performance evaluation of the retrofitted structure, and this time we can see the removal gets to the end before any other failure occurs. Axial forces distribution shows a greater participation of the external columns and a consequent lightening of the adjacent ones. And we can see tension forces on the high floors are rising above the columnar removal, and this could be very dangerous because it could trigger unexpected collapses. This is the analysis results with an infinitely stiff roof truss. Even if it's only a theoretical situation, it allows interesting considerations about the limits of the redistribution strategy proposed. The results are the same, but they're enhanced, so even more good load redistribution and even higher dangerous tension forces on the top floors. So coming to conclusions, the model, well calibrated against experimental results, was able to well simulate progressive collapse scenario. Original structure revealed the need of retrofit and the need of better redistribution, increasing the participation of the column distant from the removal. A good redistribution is achievable with a properly designed stiffness of the roof truss, but with stiffness at the same time, tension forces in the top floors columns rise, which could trigger failure mechanisms. On the simplified model, it was found that the roof truss stiffening grows both with the area of the profiles and the height of the truss with some limits. The application of these results to the case study allowed to identify a range of available heights and to select the value which best allowed the structure to achieve the target performances. And the results of the analysis showed that the proposed system can effectively protect the structure by increasing safety against progressive collapse. Our current work concerns a direct development of this job. We have just investigated the performance of the original structure through nonlinear dynamic analysis. Here you can see the results in terms of displacement above the removal and axial forces with the time of the analysis coming out from incremental dynamic analysis. Nonlinear dynamic approach was useful for both validate the static design procedure, as we were just talking about before, and also for correctly and effectively evaluate the diff, the dynamic increasing factor, which is the key parameter for progressive collapse analysis. We evaluated the diff numerically and directly because UFC guidelines concerning the diff in this case were not on the safe side. This because the formulation proposed in the code has been calibrated based on a beam type collapse, whereas in our case study was subject to column time mechanism first. Moreover, thanks to the dynamic approach, we also proved that the introduction of a properly designed roof truss can reduce the dynamic amplification factor, as you can see here in the figure, which strongly helps the retrofit. Finally, as potential future developments, all the case study with different collapse scenarios should be considered, whereas introducing a three-dimensional roof truss could lead to an even higher redistribution in a safer way, probably. Thank you for your attention.